We are now recording. Let's get the first slide up, though you won't be able to see it till the projector warms up. But let me go over just a couple of announcements. One of these, I hate to say this, but I sort of doubt if the summer schedule is going to come out quite as scheduled. I don't know when it's supposed to be released, but when I talked with my boss this morning, they still hadn't decided how they were going to run the summer schedule. And they say, yeah, but your schedule's due by the 1st, which is a Sunday. And I thought, well, what are we supposed to put on the schedule? Well, I'll try to find out. So I don't know. It may be, I hope, a little late coming out. And one reason I know mine will be late, or at least I suspect it will, is that last Friday, I don't think I announced that I wouldn't be on campus because I had a meeting down in Opelika. So we didn't turn out to be as long a day as what we had feared, but it still was long enough, about a 9.5-hour day. And since I'm only supposed to work 4 hours on Friday, so I usually do work more, I asked my boss if I could have this Friday off too, since I put in 2 Fridays worth plus last time. He said yes, so I'm not going to be in on this Friday either. We have some things we have to take care of, and it's just I was going to have to take 4 hours off Friday anyway, but now with me already working 4 hours, he said I'd go without it. So anyway, that's where we, that's the one thing I know is coming up for this time. I just was wondering, are you planning to be here in the summer or not?
No, I graduated in May.
You graduated in May, okay. I didn't know if you're going to take a few more courses in the summer or not, but no. Okay, that's beside the point. I just was wondering. Are both your brothers too, or do you know?
I think Jonah is going to have to take calculus 2 this summer.
Oh, okay. Because he's computer science, and our computer science program didn't list it here, but his receiving school did. Yeah, okay. All right. Well, I didn't know if you were going to try to do either linear algebra or differential equations here, but you're going to take it at your next school.
Do you think I should?
Typically, we have smaller class sizes, and actually in the summer, the classes are probably a little more likely to make because we get transient students from other schools coming in and taking them. But I don't know. That's up to you. And then I don't know how they do in the summer schedule. You know, if they do what they're saying now, or the last I heard was, well, we're going to keep the schedule the same as last summer, which is a 10-week normal summer term, but we're only going to teach it for 8 weeks. I said, well, that's not going to be enough hours. He said, well, just give extra assignments. I went, what? You know, that's not teaching, that's giving extra homework, you know, so I don't know. I still haven't heard an answer on that one yet, so it may be not a bad idea, but then too, it may be really cramped this summer. I don't know. And again, I don't know. I just don't know until I hear something more. All right, anyway. We were in Chapter 12, Vector Value Functions, 12.2, Differentiation and Integration of Vector Value Functions, and this is example 3. It says, find the intervals. Oh, did you have any questions first? I should have always asked that. Okay. Find any intervals, or find the intervals, or let's see who's coming in. Oh, Fred decided to show you there. That's good. And we're just starting example 3 on page 830 in section 12.2, chapter 12, of course. Find the intervals on which the epicycloid C, though we don't use that C anywhere, given by RT is equal to 5 cosine T minus cosine 5T I plus phi sine t minus sine phi t j, when t is between 0 and 2 pi, is smooth. Find the intervals on which that epicycloid is smooth. Okay? Now, what do we mean by smooth?
No edges.
Second, no edges. Okay. No cusp, no corners. That's if we graph it and look at it, which we probably are going to wind up doing too. How would you be able to tell calculously, you know, what's true about that, or that, or that, or, you know, a place that is edgy, or cuspy, or cornery, as opposed to ornery. About, as in differentiation. So problem with that with derivatives. Here the derivative would be very positive. Here it would be very negative. Well, it's discontinuous. Where your first derivatives would be discontinuous. That's going to be a problem. And that would result in non-smoothness. Just about always, I would think. So guess what we would do then? Oh, sounds good. Okay. Let me get my pen set up. There we go. And we'll do R prime of t. What would that be?
Negative phi sine plus sine phi.
5 what?
Phi sine phi.
Sine of 5t. Okay. I don't hear well, sorry. I plus J. Okay. Now, well, with vector functions, it's not quite as easy to see. Okay. All right. I agree with what they're doing here, but it's not, and maybe I'm just being dense about it, it's not completely clear why they're doing it. They say on the interval 0 to 2 pi, which is what we're looking at, the only values of t for which r prime of t is the 0 vector are these. Well, that would give places where the first derivative is 0, where you have horizontal tangent points. That doesn't guarantee is non-smoothness. So I don't see why they're starting that way. Sorry. Let's go back. Forgot this. This was the last slide we had last time. The parameterization of a curve represented by the vector value function R of t is equal to f of ti plus u of t j. We don't have an h of t in this problem we're doing now. Is smooth on an open interval I when f prime, g prime, we don't have an h prime, are continuous on I, which I certainly were, but and r prime of t is not equal to 0 for any value of t on the interval. So that's what we're looking for. That's why they went back and did this. I had forgotten that, because when r prime of t is the 0 vector, that's basically saying your first derivative has, I want to say disappeared, but that's not quite true. Your x and your y derivatives are 0. The derivative of the f function and g function, of the I functions and j functions, are both 0. And where that's the case, in effect, your first derivative have disappeared. I mean, because what is the 0 vector? It has no direction, no magnitude. It's nothing. So that is the place, and that's why, forgetting that, we look at the places where these are 0. So let's do that. I'm going to rewrite this as 5 sine of 5t equal 5 sine of t, right? If you set that equals 0, the first one, f equals 0, this is what you get, right? Okay, and then divide both sides by 5 would be legal, and that would say the sine of t equal sine of 5t. Now, I don't know any particular identity that is going to relate those two, but I can tell you one thing: this is equal to 0 when t is equal to 0, right? And this one certainly is equal to 0 when t is equal to pi, and that will be 2, right? Because any whole pi, so 2 pi, 3 pi, 4 pi. So these are zeros. Your f function here, the f prime function here, is 0 at your whole pi's. Okay? So this will be, and since you include this, at t equal 0, pi, and 2 pi. Okay? This thing will be 0 then. Okay? Now, are there any other places where they would be equal? Well, let's go on to the second one and do something pretty similar. 5 cosine t equal 5 cosine 5t. Okay? And again, that's an ugly 5, but we can divide out the 5's, and where the cosine t is equal cosine 5t. Okay? And well, of course we know that all your cosines are zeros at the half pi's. And if the t equal any half pi, 5t is also going to be a half pi. Okay? So that would be at t equal, or these are equal 0 at t equal pi halves and 3 halves pi. Okay. 5 halves pi would be too great. Now, the question is, we know that these are zeros there, but none of those points are in common. Now, it would be nice if this one were 0. Now, all that required here is this to be 0, which these would be equal. Well, let's see at the half pies. When t is equal to pi half, sine is 1, okay? How about at 5 halves pi? 1 half pi, 2 halves pi, 3 halves pi, 4 halves pi. Wait, I'm sorry. 1 half pi, 1 half pi, 2 half pi, 3 half pi, 4 half pi, 5 half pi. Right? That would be 1, 2, and 1 is equal to 1, so that would also be. So the half pi works there, doesn't it? It works over here too. Okay? How about the 3 halves pi? 3 halves pi, 6 halves pi would be 3 pi. 9 halves pi would be back up here again. And going to 15 halves pi, that would be 12 halves pi. Well, that would be 6 pi, that's a multiple of 3 pi. I'm lost here. Okay. 3 halves pi, 6 halves pi, 9 halves pi, 12 halves pi. And would that be 5? Yeah, that would be 5 again, but that would be 15 halves pi here. And that's where we started. So again, they would be equal to each other, and we know they're both equal to each other there. So this would also be 3 halves pi would work here too. All right. Now, it would also be required that these work over here as well. Well, what is cosine at 0? Yep. 1, and then cosine of 5 times 0 is still 0. So certainly 0 works here too. So 0 works there. How about at pi? What's cosine of pi? Second? I don't think so. 0. Negative 1. How about at 5 pi? 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. Negative 1 again. So yeah, it will work at pi. Okay. How about at 2 pi? Will it work there? Cosine of 2 pi is 1 again. And at 10 pi it would be 1 again. Yes, that certainly would. Well, that's the same as 0. So they work at 1, it would work at the other. So yes, at those 5 values, they're all 0. I mean, okay. They're the same. This thing in here is 0. And this thing in here is 0. So those would be at least 5 places. Well, those are at 0, pi halves, 3 halves pi, 0, pi, pi halves, pi, 3 halves pi, and 2 pi, which again is the same as 0. So those would be on the axes, okay? And both of them would be 0 there. So certainly that would be the conclude that C is smooth on the intervals in between those. So, because those are the, now what we haven't shown is they're the only places there's zeros, but I think you can kind of deduce that just by the periodicity of them, that that's going to be the only places they're going to be the same. So, on the interval from 0 to pi halves, but then not at pi halves, from pi halves to pi, but not at pi. From pi to 3/2 pi, but not at 3/2 pi. From 3/2 pi to 2 pi. In between that, they will be smooth because both of them aren't 0 at the same time there, but they are at those 4 points. And these these 4 intervals. They're non-zero. At those points, they are both 0, so they won't be. Now, let me clear up what we've written and see if this is adequate for what they've said. Okay? The derivative of your R function is exactly like you had it. And on the interval there, the only values for a t which that derivative is 0 in both cases are these. Now, we showed they were 0 here. I don't know that they've shown that the only values would be those values. That's where I was sort of getting stuck. But like I said, from the periodicity and stuff, I think that almost it can be shown that. We didn't show, but they just said it was so. So we'll go with their statement. Okay, so therefore you conclude that C is smooth in the intervals other than the axes, quadrantal angles. So it starts here and definitely is not smooth there. It is smooth from there to there, again from there to there, there to there, there to there. That's why these are open intervals only, not closed intervals, because it's not smooth at that point. I don't know that was all that enlightening, but is pretty interesting. A 4-leaf clover, nevertheless. Okay. Now, in figure 1210, the curve is not smooth at the points where it makes abrupt changes in direction. Such points are called cusps, which we were calling them, and sometimes nodes, which we didn't use that term, but that's another term for it. All right, so here are, in our theorem 12.2, the properties of a derivative. Let R and U both be differentiable vector value functions of the parameter t. Let W be a differentiable real valued function of t. This is a scalar function. R and U are vector value functions. So W is a differentiable real valued function of t. And C is any old scalar, any real number. We're keeping them real numbers and so forth. So, here are the properties of a derivative. d by dt, fun to say that, isn't it? Of C of R of t, what you can do is just pull the C outside the derivative and then take the derivative of R of t, which is R prime of t. Same rule that we had for scalar functions. And derivative of the sum or difference of two vector value functions, differentiable vector value function, is the sum or the difference of their derivatives. Same as for scalar functions. The d by dt of a scalar function multiplied by a vector function. Okay? Now this is a type of a product rule, but you're multiplying a scalar function times a vector function. And the rule holds. First times the root of the second plus the second times the root of the first. Okay?
So W is a scalar?
Say again?
W is a scalar?
That would be what?
Is W a scalar?
This is a scalar function. That's a vector function, but the product rule holds. You know, they're both functions of the same parametric variable t. Okay? So, and is your question, is the answer a scalar? Is that what you're asking?
I was asking because you said W is a scalar.
W is a scalar function. It's not a scalar number, but a scalar function. Its values is a number, not a vector. Now, there's two types of multiplication of vectors. vector to vector, that's a dot product and a cross product. Well, the derivative of a dot product, guess what, is a product rule of the two vector functions. The first vector function times the derivative of the second vector function plus the second vector function times the derivative of the first vector function. Just like, I don't know if you were expecting it, but just like is true for the product of two scalar functions. How about the cross product? Okay? Now, time out. Would it have mattered if we had done R of t times W of t? No. Okay? Would it have mattered if you did the second time derivative of the first plus the first time derivative of the second? No. In either of these cases. However, with cross product, the order matters. Okay? So remember to do this. When you're crossing R of t with U of t, both vector value functions, you can't cross product any other kind, then it's R times cross U prime plus R prime cross U. And again, you can't say first, second cross the derivative of the first. It has to be derivative of the first cross the second. You have to get the order right, because if you flip the order, you negate. Okay? So that's why you can't flip these. That would be a negation. And you can't flip those or those. Either of those would be a negation. So you have to keep the order as it is. Now, this one, you could do derivative of the second, derivative of the first cross the second, plus the derivative of the first cross, I said that backwards. Derivative of the second, the first cross the derivative of the second. You could do that one because addition of vectors is commutative. Cross products are not commutative. Okay. That. Now, number 6. This is sort of like a chain rule. Composite function of a vector function composed with the scalar function. Let me first get Dawson here and Josh here. Okay. We're only missing Ryan then. All right, we're doing the properties of derivatives, the bottom of page 830, chapter 12, vector value functions, 12.2, differentiation and integration of vector value functions. We're down here at number 6, the derivative of the composite of a vector value function composed with a scalar value function. Hopefully, just like you would hope it would be, derivative of the outer, which is the vector value function, evaluated at the scalar function times the derivative of the scalar function. Okay? Good old chain rule when you have a composite of a vector value function composed with a scalar value function. Notice they don't do the reverse. Because what in the world would it mean to have a scalar value of a vector value function? That kind of doesn't make sense. The only thing you can have a scalar value function of is of a number, a variable. Okay? So you can't reverse these. Okay? That really just doesn't make sense. But when you keep them in that order, that's what you get. Now, number 7. If the dot product is, of course it is, the dot product of two vector of the same vector, if R of t dotted with itself is some constant c, which it will be. In fact, you know what constant that will be. The magnitude of R of t squared. Remember? We did that in an earlier slide. Okay? So that is going to be true. If R of t dotted with R of t itself is some scalar function c, then R of t dotted with its derivative, okay, is always going to be 0. Since this is always going to be the case, the only case I can think of where it wouldn't be if R of t was the zero vector. And then it really doesn't make any sense anyway. And that number would be 0, and this wouldn't even make sense then, I don't think. But you can't take the derivative. So anyway, that's going to be the case there. Number 7. I can't think of a counterexample to it, so I think that would be the case. They prove property 4. That's the dot product rule, you might say, derivative of dot product, which would be that. So they show that here. I'll let you go through the proofs. Let's see if they do example 4 and we'll actually use them. Yes, we do. Look at this. Now, here is your vector R of t, which is 1 over 2I minus j, plus log tk, see that. The u vector, okay, needs to be 3-dimensional. Sure enough it is. T squared I, minus 2tj plus k. Find each of these derivatives. So let's do the first one. Do you want to do it 2 different ways, or you want to just do it one way? Okay, let's do it. Which way you want to do first? What were you thinking when you said 2 ways? You just said 2. Okay. All right. Here's what I mean. We could take the dot product of these two, which is going to be a scalar function of t, and then take the derivative of that. Or we can use the rule we just did, which is also going to give us a scalar value. Okay? So, which you want to do first? Do the dot product first. So let's first do R of t dot u of t. And that's a pretty easy one to do. What would that give you? Anybody? Okay. You multiply the corresponding components together and sum them up. What do you get for the first one? T. No, you don't have i's anymore. This is a dot product. Okay. T. Not that bad, I don't think. Plus 2t. Strange last one. Not too strange, but log t. That is our dot product. Now, well, let's combine like terms. What does that give us? 3t plus log t. And then let's take a derivative of that. d by dt of that would be okay, that's our answer doing it that way. Now let's do it according to the fourth property we just had there. Okay? Now perhaps what we need to do in advance of that is to do our calculations. I'm going to, just because that's sort of in the way, I'm going to rewrite this as d by d, well, I'm just going to rewrite the answer here as, just remember, that's what we got last time. Okay. Now, what did our property that we just did tell us this was going to be? Oh, I forgot. It said we were going to take the derivatives, r prime of t. What would that be? With a minus in front, right? Okay. I, because this is a vector. What's that? 0j. Okay. Anyone remember what? Second? 1 over t k. It's also a vector. Let's do our u prime. This would be 2ti minus 2j and 0k. All right? So, you tell me what d/d, it's not fun to say, of rt dot u of t. It really doesn't matter on this one which way you go first. How do you want to do it? Where do you want to start? Okay, what we're doing, we're using this rule here to calculate that dot product. The same thing we just did, but we're using this rule to do it. So r dot u prime plus r prime dot u. Right? This is, to me, the harder way, but I think this is the way they wanted you to do it. We did it the easy way. Let's do it this way then. So what is that one again? Doesn't matter which one you go first. Second? R. I'm just going, yeah. R dot u prime. Is that okay? Plus what? Plus r prime dot u. Okay? Now we know what r is. I'm going to write it in angle component notation just because I don't like writing all those extra things. 1 over t, comma, minus 1, comma, log t, dotted with u prime was, you tell me. Two t, comma, 2 minus 2, comma, 0. Perfect. And we're going to add to that the dot product between negative 1 over t squared, comma, 0, comma. I think that's just a 1 over t. My writing is pretty bad, but I think that's right. 1 over t. Yeah. Where did that go? Whoa. Okay. All right. Now we've got to do those two dot product. Whoa. Missing something. That's your r prime. We didn't dot it with the u, which is t squared. Goodness gracious. Minus 2t 1. Right? All right. So let's dot those together and see what they get. These two dotted together give us, whoops, no longer a vector. Okay, you're right, 2 plus, it's 1 times 2, negative 1 times negative 2, isn't that 2? If I wrote it right, I think it is. Right? And what's the last one? 0. So, what's 2 plus 2? High level math now. 4, all right. Didn't know you'd be doing such incredible stuff today, did you? Okay, let's dot the other 2. Add to that. Negative 1 plus 0 plus 1 over t. Okay. Now something has gone terribly wrong here. Oh, no, it hasn't. 4 minus 1 is 3 plus 1 over t. Ding, ding, ding. Same thing, both results. Okay? Obviously, easier to take the dot product first and then take its derivative. Okay. At least in this case. All right. I'm just going to guess Fred's going to want to do this in this way. Okay. Oh, no, this is a different problem, isn't it? This problem says, what is the dot product? What is the derivative of u cross u prime of t? Anyone want to hazard a guess? Second? Okay. I think we probably could go that route if you wanted to. Please say you don't. Okay. Let's look at property number 7 on the previous page. Now there's a caveat there. If u dot u is equal to c, well, I think it's got to be, doesn't it? U dot u would be t to the 4th plus 4t squared plus 1. Okay? And for any value t, that's going to be some number c, right? So what does it say about... Oh, I'm sorry, I misread the problem, didn't I? But I think it's still true. No, it's not still true. Ah, that's a dot, not a cross. Sorry about that. Way off. I think we do have to do what you were just saying. Do you want to do this one way or two? Huh? Okay. I think they want us to do it the way the number 5 did. So let's do it. And you're right, you will have to do a second derivative. Thinking back on what you said. So what do we have here? Let's just deal with the u's to begin with, and then we'll go back and plug in what u is or u are or whatever. Using number 7. I'm sorry, not number 7, number 5. What does that tell us this will be? u of t cross double prime of t plus u prime of t cross u prime of t. Now, that goes back to something we did earlier. You know what a vector cross itself is going to be. Like this u prime cross u prime. You remember that? I think we're going to have to go back to a much earlier chapter. I don't think it's anywhere in this one, unless they just remind us. I don't think they do. All right, let's see. Yes, the zero vector. When you dot two vectors in the same direction, you get the magnitude squared. When you cross two vectors in the same direction, you get zero. Okay, the zero vector. You're right. So we know what this one is, the zero vector. Okay? So we already know what u is. We had just calculated, and unfortunately I erased what u prime was, so tell me again what that is. 2ti minus 2j plus 0. So what would be u double prime of t? Help me. Help me. 2i, right? Yay or nay? Yay. All right. So let's do what they just told us to. Your u of t was t squared. I'm going to write it in component notation just because it's so much easier. T squared minus 2t, comma, 1. And we're going to cross that with 2, 0, 0. Okay? How you want to do it? I, J, K, I, J, stop. Okay? What do you put in there? T squared minus 2t, 1, t squared minus 2t. Okay? Okay. And 2, 0, 0, 2, 0. Now that's not really a... Why am I going blank? Discriminant. That's not it either. Determinant. Okay. But we'll pretend it is. What would be your first component? 0i. 2j. Plus 0k. Plus 4t k. That's it. 2j plus 4t k. Let's see if that's what they got. Oh my goodness, yes it is. That's what they got. All right. Now, I think I can safely say it would be far easier doing this one this way, using the property first and then taking the cross product, than it would have been crossing, well, first taking the derivative of u, which wasn't hard to do, crossing that with u cross its derivative, and then taking the derivative of that, I think this comes out being an easier way to do it. So you can't always say, always do it this way. Never say never. Okay. Any questions on that? Let's watch them do it and see if they did anything any differently. Okay, for the first one. Because r prime of t is minus 1 over t squared I plus 1 over tk, exactly what we got. And u prime of t is 2ti minus 2j, exactly what we got. Then d by dt of r dot u would be r dot u prime plus r prime dot u, just like we did. And then when you dot those together, they're doing it the second way, which I thought that's what they would be doing. Oh, man. This was our original R, which is not shown on this slide. You have to go back and look at it. Dot your U prime, which is shown here, plus the R prime, which is right here, dotted with its U, which isn't shown here, but that's what it was. And then you do the dot products. This gives you 2 plus 2 plus 0. 2 plus 2 is 4. And this gives you ti minus ti, sorry. No, it doesn't. It just gives you minus 1 as a left square. Minus 1 plus 0 plus 1 over t. And that would give you what we got, 4 minus 1, 3 plus 1 over t. 2 plus 2 minus 1 plus 1 over t, 3 plus 1 over t. Just what we got, the easier way, and that way. Now doing the second one, again, you know what? Yeah, you know what u prime was, though we do need it here. No, we sort of need it here. And u double prime, we got to do that exactly like before. Then the d by dt of this would be u of t cross u prime, u double prime of t plus u prime cross u prime. Okay. Now, they just jumped to the case without saying it. Well, yeah, they did that. They said this is the zero vector. So this will be your ijk. U, which they don't show here, was t squared minus 2t plus 1. Okay? And then the u double prime was 2, 0, 0. And actually, I'll give you a hint here. Doing just the derivative part here, this is a determinant here, okay? In doing just the determinant, it's actually easier doing it this way than the way we did, okay? Because you see, no matter, okay, and y'all, not even these two who are taking linear algebra have we gotten to this part of doing determinant. But when we get there, you will know this. To do a determinant, pick the column or the row, it doesn't matter which, with the most zeros in it, which would be this one. And then do your determinant just with that element right there, okay? And this is in the plus position, plus minus plus. So 2 times the cross product here, which would be j plus 2tk. So 2 times j plus 2tk would be 2j plus 4tk. And that's exactly what we got. This will give you a 0. And it's ridiculous how they did this, but that would give you a 0, so this would be a plus 2j, and this one would be a plus 2tk, which is what I got too. I'm sorry, 4tk. Yeah. And that's what we got. Every way we did it, 2j plus 4tk. All right, that was example 4, A and B. Now we're moving to integration of vector value functions. Now, how do you reckon we integrate vector value functions? How do we differentiate vector value functions? By components. That's how we integrate vector value functions. By components, exactly. Do everything by components, okay? The following definition is a consequence of the definition of derivative of a vector value function, but now we're going to undo that and do the integration. Definition of integration of vector value function is R of t is f of ti plus g of t j, and f and g are both continuous functions on some interval a to b. Then the indefinite integral, or the antiderivative of r, is the integral of this will be the integral of f times I plus the integral of g times j. Okay? Now, notice we say f and g are continuous. If they're continuous, you can integrate. Okay? If they're discontinuous, I would hesitate. Okay? Notice I didn't say integrable functions, just continuous functions. They are integral. Okay? And the definite integral over an interval from t is going from a to b would be the integral of a to b of r of t dt would be the integral of a to b of f of t dt I plus the integral of from a to b of g of t dt. So the indefinite integral, just leave off the endpoint, definite integral put in. Now, if R of t is a three-dimensional space vector, same thing, you just throw the h in there as well. Indefinite integral would just be that. You just add the integral of h of t dt k. Definite integral, just add the integral from a to b of h of t dt k. Now, there's one other sort of little issue here, okay? Remember when you're doing indefinite integrals here, you're usually going to wind up with a plus c, right? It's not the same c for this one and that one and that one, so you'll have either C1, C2, and C3, or CDE, or something else, but you will have those indefinite integrals require you to include your constants in there. You didn't have that to worry about with differentiation. You just have to keep it in mind for integration. So the antiderivative of a vector value function is a family of vector value functions, all differing by some constant vector c. Because notice it had a c1i plus a c2j plus a c3k. That adds up to some constant vector c. And they put a bolded the c there. And capitalized it for some reason. For instance, if R of t is a three-dimensional vector value function, then for an indefinite integral, the definite integral that you don't have to worry about. Indefinite integral, the integral of R of t dt, you obtain three constants of integration. This will be some f of t plus c1, some g of t, capital G of t plus c2, and some capital H of t plus c3. Then the where capital F of t, derivative of that is your little f of t, capital G of t, derivative, these are just the antiderivatives. Would that be the case, then the three scalar constants produce one vector constant of integration. So this will be an f of t, some variable f of ti, g of tj plus h of tk plus c1i plus c2j plus c3k, which is some capital R of t, which is the antiderivative of little r of t plus some constant vector c, where this one derivative is, of course, that antiderivative. Okay, like I said, that's the only thing you really have to worry about. Let's do example 5. Oh, what do you think the indefinite integral of this integral here would be? Take as many steps as you need to do it, or as few steps as you might need to do it. What do you think this would come up with? Anybody? Make a stab. Got it?
Plus
3t. One thing else. J plus some vector c. Two-dimensional vector c. And if you want to just leave it like that, you can. Okay? You could have said this is plus the C1i and this is C2j, and then the C1i plus C2j is your two-dimensional vector C. Or just put it as its own vector there, the constant. Okay? And that's exactly what they got. T squared over 2i plus 3tj plus some vector c. Let's see how they got it. I think they'll probably take a few more steps than you did, which is fine. Integrate component by component. So you can rewrite the well, that's what we did. That's exactly what we did. Integrate this, you get t squared over 2i, integrate that, 3tj, and then put some constant vector out there that covers the I and j components of your integration constants. Whoa! That's the last slide in the section. But it's not the last example in the section. We have at least 6 and 7 to go. Yeah, we have exactly 6 and 7 to go. So let's back off here and do example 6. Evaluate the integral. The integral, remember, 0 to 1 r of t dt. You tell me what 0 and 1 stand for. The limits of t. Okay? These are the values for t. Whatever the t is, t equals 0 to t equals 1. Okay. Just like regular. But just to remind you, it's not r or anything else. Okay, here's what the definition of that is. The integral from 0 to 1 of the cube root of t times I plus 1 over t plus 1 j plus e to the minus t k dt. There's your r vector that we're integrating. Okay? Is there anything you want to do first?
you can make for the I value, make it t to the 1/3.
Yeah, I like that idea. So I'm going to do integral from 0 to 1 of t to the 1/3 I. Want to leave that alone or do something to that too?
You could do t plus 1
t plus 1 to the negative 1 j, and then leave this one alone, plus e to the minus t k et. All right. Now that you've done that, what would you do next?
So it would be t 4/3 over 3I.
Okay. Okay, you said 4/3 over 3?
Yeah, like t over 3 and t over 4/3.
Okay, let me see. You're saying t plus t to the 4/3? I missed it.
So I'm saying t to the 4/3, and then t is over 3.
Okay. Wouldn't it be over?
It would be t divided by 1/3.
Okay. Oh no, okay, it's your whole exponent. Your second?
So it's
Over 4/3, which is the same as,
times t to the 4/3.
but it's over 4/3, which is times 3/4.
Okay.
By that?
Yeah.
Okay, I got some swampland down in Florida, I'll show you that. Okay, now. Okay. And that'll be the I part. Well, okay. Here's how I kind of like to do it. And you don't have to, it's just my preference. Evaluate this from 0 to 1, and that will be the I part. Okay? Let's just sort of pretend we're breaking it up. Okay? Next. I'll take off my sign and let you tell me what to put.
Will you do a use substitution?
What's this again?
Will you do a use substitution?
You could. What would you like to substitute?
U is equal to t plus 1.
Okay. And then what would you have?
U to the negative 1.
Yeah. And what would that be?
That would be U to the 0.
Over 0.
So you 1.
Yeah, over 1. Over 0. Which would be not a good thing at all. What is antiderivative of what you were calling 1 over u? Log u. Okay, so this would be log of t plus 1. Now, normally I'd put absolute values. I'm just going to put t plus 1 because we're going to evaluate that from 0 to 1. And that will be your j part. Okay, then what?
This would be plus e to the negative 2.
Anything else?
Okay.
Huh? K here. Well, I'll put my 0 to 1 here too, and put my k there, but what else?
That would be a negative.
It'll be a negative. Okay. I left that blank for a reason.
Why is it negative?
Because chain rule, anti-chain rule. Not anti. Yeah, anti-derivative, anti-chain rule. Well, here's the other thing. Take the derivative of this. What do you get? Minus e to the minus t times the minus 1 plus t. That's probably the best. Okay, now let's do our evaluation. Anybody? 3/4. I. That's yes in Navy speak. Okay. Second. ln of 2. Which is 0. Okay, so we just got ln2, whoops, j, don't forget that, okay? Next, minus okay, I'm going to write it as 1 over e. Yeah, okay. In parentheses, minus 1. These points here, you have to be very careful about parentheses and minuses and things like that. Minuses are only there to trip you up. That's their only function in life, is to trip you up. And this was about to do it, wasn't it? Okay. Because it's a minus in front, then the first minus the second, and that would have been a minus 1, and this would be your k. So written a little bit neater would be 3/4 I plus log 2j, one of my favorite numbers in the world, and then this one would be plus 1 minus 1 over e k. Now, you don't have to write it that way. I just did. Let's see what they got. 3/4 I plus log 2j plus 1 minus 1 over e k. Yes. Okay. And you see, you don't have a c because this is a definite integral, so you've already taken care of that. All right. So that was example 6, and we got what they did. I'm ready to move on to example 7. They do have a little comment here. As with real-valued functions, you can narrow the family of antiderivatives of a vector value function r prime down to a single antiderivative by imposing an initial condition on the vector value function. Oh, okay. We're going to do that next. So here's what we're going to do here. Find the antiderivative of, this is example 7. I should have asked were there any questions on the last one, but y'all didn't seem to have any, did you? You're okay with it? Okay. I usually ask, I forgot to. Find the antiderivative of this. We're told that r prime of t is equal to cosine ti. I like to put those in parentheses. They put some in, like that log 2 and the one above. That was pretty obvious to me. This one, not quite so. Okay, only that's log of 2ti, isn't it? If I could read. Minus 2 times the sine of tj. And I think I'd like to put that in parentheses, sine of tj, plus, this one I think will be all right to stand by itself, 1 over 1 plus t squared, is it? And that will be k. All right. That satisfies this initial condition. R of 0 is equal to 3i minus 2j plus k. Now, tell me again, what does this 0 represent? Second? When t is equal to 0. That's exactly what it means, okay? So, we're to find the antiderivative of that r prime, which would be r of t, I take it, and that would be, how do we find antiderivative? Indefinite integral of cosine 2t I minus 2, I'm going to put it like this, times the sine t j plus 1 over 1 plus t squared k. Okay. Evaluated. We're going to evaluate it at 0 to get our constants. Okay. Oh, wow. What's that first integral? Component by component. Help me somebody. Okay, certainly will have a sine 2t in it. Huh?
Sine 2ti.
Okay. Anything else in there? Not a negative. To right, leave that positive. Because derivative of sine is positive cosine. But you have to undo a chain rule, which means, second? Divide by 2. Perfect. Okay? Because you're undoing the chain rule. And you're taking a chain. What's that?
Chain will be multiplied by 2.
Yes, and you're undoing it, you divide. Exactly. Okay? Minus, well, you tell me, plus 2 cosine t j ooh boy, what is this one going to be?
Is it the natural law?
Nope. Uh-oh, way back. Cal 2. This is going to be one of those trig substitution ones. You see, even for natural laws, you would need a 2t in the numerator. You don't have, or a u substitution, but this is going to have to be. Does anyone remember what trig substitution would yield you that? So let's come up here and do a little scratching. Okay, since there's no, never mind, okay. Integral of 1 over 1 plus t squared dt. Okay, anyone want to make a guess? How about that one? Now, how I remember these is, think of, I don't know if this is the best way to do it. This is how I do it. I think of my Pythagorean identities, because you got a square here. That leads me to think it's got to be a sine, a trig function, okay? And 1 plus what squared is going to be another trig identity. Second?
Sine squared plus cosine squared is 1.
I can hear you. You may have said it right.
Sine squared plus cosine squared is 1.
Okay, but if you then solve for 1, that would be a 1 minus t squared. So that sign wouldn't work there because the sine squared plus cosine squared is equal to 1. So
Isn't it like 1 plus tangent squared is
that's it. That's why I choose the tangent.
Is it secant squared?
Yeah, secant squared. That's exactly right. Okay? So if you let t be the tangent theta, then, of course, the next thing you got to do is dt is going to be, help me somebody, derivative of tangent theta. Secant squared theta, okay. All right, but then we also have to square, because it's not t, it's t squared. So t squared is going to be, if t is tangent, t squared is tangent squared theta. But then you got 1 added to it, so 1 plus that would be 1 plus this. And what that's going to be? You just told me. Secant squared theta, right? 1 plus tangent squared is secant squared theta. Okay. And I do believe we're ready to do our integral then. The integral 1 over 1 plus secant squared, 1 plus tangent squared theta, 1 plus t squared has become secant squared theta. Oh, I left off my d theta here, okay. And the numerator, the dt, is going to be secant squared theta, d theta. Whoa. And that's going to be the integral of d theta. And what was that going to be? Anyone want to make a guess? Well, 1 theta, right? Yeah. Okay. Plus some constant, but we'll worry about that later. Well, what in the world is theta? Well, we had up here what tangent theta is t. So what is theta? Let's undo a tangent. What do we have? Arctan. So theta is equal to inverse tangent of t. So that's what this one's going to be. Plus inverse tangent of t. Okay. Okay. But we've got our plus C1, C2, and C3 we didn't do, did we? So let's do this. Plus C1, plus C2, and plus C3. Now I'm doing them that way rather than the other way because I think in this case it's a little easier to do. Okay? And we know that R of 0 is equal to 3I. So if we plug in R of 0, that's equal to what? What sign of 2 times 0? Second? 0. Okay. So this would just be C1. Okay. Well, then I think that C1 has C1I. Okay. Let's go to the next one. Plus, when you plug in cosine equals 0, what do you get there? 1. So that would be 2 plus C2 J, right? Plus inverse cosine, inverse tangent of 0. Anyone remember? 0. So you get C3K. And this is supposed to equal 3, negative 2, 1. I'm tired of writing the I's, J's, and K's, so I'm really mixing up the notation, but hopefully, anyone want to make a guess what C1 is? 3. How about C2? Negative 4. And C3? You're doing so well. 1. Okay. So let's go back and write what our solution is. Let me write R of t is equal to. Now, I'm going back to integral notation. Component notation. Okay. This is sine 2t over 2 I 2 cosine t j plus inverse tangent of t k plus the vector 3, negative 4, 1. You could have written each of those with that, but it sort of seems like a little easier to just do it that way. Let's see what they got. They wrote it the other way, sorry. R of t is equal to 1/2 sine of 2t plus 3i plus 2 cosine t minus 4j plus arctan, they like arctan, I like inverse tan, of t plus 1k. Okay. That finishes 12.2. Okay. By the way, the concept checks are here, and good reason to look at them is they do review the concepts for you. And if you need help with some of those, at least the odd ones are at calcchat.com. But then the actual exercises are any of the odds 3 through 9. They're all at CalcChat. 5's at CalcView. Any of the odds 11 through 17, they're all at CalcChat. Either 19 or 21, both at CalcChat. Either 23 or 25, both at CalcChat. 23's at CalcView. Any of the odds 27 to 33, all at CalcChat. 27's at CalcView. 35 is both at CalcChat and CalcView. Now I've got to see what they're doing here. Oh, you have 6 things to find. Okay. Using 6 of those properties. So 35's at both at CalcChat and CalcView. 37's at CalcChat. Any of the odds 39 to 45 are all at CalcChat. 41's at CalcView. 47 through 51 are at CalcChat. 47's at CalcView. 53 through 57 are at CalcChat. 53's at CalcView. You can explore doing 59. It should be at CalcChat. And then some proofs, good old proofs. 61 through 67 should all be at CalcChat. 69 and or 71 should both be at CalcChat. True false 73 and or 75 should be at CalcChat. And that finishes 12.2. Any questions on 12.2? All right, to erase my screen. Okay. And okay. We will go to 12.3. Now 12.3 will be at the midpoint of chapter 12, which means chapter 12 test is coming up, not super soon, but somewhat soon. So need chapter 11 test in as you can get it to me. All right, let's go from current slide. We're still in vector valued functions, chapter 12. 12.3 is velocity and acceleration. Our objectives here are to describe the velocity and acceleration associated with a vector value function, and we'll use the vector value function to analyze projectile motion. Okay. As an object moves along a curve in a plane, okay, we're in a plane right now, the coordinates x and y of its center of mass are each functions of time, t. It's so convenient that we were using as our favorite parameter t, and now when we move to actual physical examples with velocities, accelerations, and displacements, our t will represent time. Rather than using the letters f and g to represent these two functions, the x and y function, it's convenient to write x is equal to x of t and y is equal to y of t. And I'm so glad they're finally doing that. In the past, mathematical purists hated doing that and always wanted you to name a function not using the variable name. But we all did it because it was so much easier to keep track of what was what. So the position vector r of t takes on the form of r of t is x of t I plus y of t j, which to me makes so much more sense. Okay? It's I don't have to remember which one's alpha, especially if they start pulling function names out of the air using some Greek ones or whatever, keeping up which one stands for the x and which one for the y. Pretty obvious which one does here. So this is in a plane, there's your position vector. Okay. To find the velocity and acceleration vectors, and they will both be vectors as well, at a given time t, consider a point q, which is x of t plus delta t, some little amount of time further on from what p was, y, t plus delta t, a little bit further on from what y was, that is approaching, now it's getting closer to p, which is x of t, y of t, along a curve c given by this equation, vector equation. R of t is equal to x of t I equals y of t j. Now, here's your point P. That's where R is at time t. Okay? Q is over here somewhere, and there's R of some t plus delta t. Pretty large additional delta t here because Q's moved all the way to there. Okay? Now, the delta R between this one and that one, in other words, this one plus this equals that, yep, there it is. There's your delta R. And as you let the t approach 0, this delta t getting smaller and smaller and smaller, delta t is approaching 0, then the R of t is going to creep closer and closer because Q is going to move along the curve closer and closer to P until they're on top of each other, and your secant vector then ultimately becomes your tangent vector at a single point. So this is when delta t is a big number, a little bit lesser number, a little bit lesser number, a little bit lesser number, and then ultimately there. Okay. As delta t approaches 0, delta r delta t approaches the velocity vector. That's going to be the vector. One thing just a little bit new here is the fact that the direction of the velocity vector is always in increasing t, which increasing time, that sort of makes sense. Okay. As delta t approaches 0, the direction of the vector pq, denoted by your delta r, approaches the direction of motion at the point time t, which was at point p. So the delta r is always the later r minus the original r, and delta r over delta t would then be that, and then the limit as delta t approaches 0 would be your difference quotient, just like we had before. That limit exists. It is defined as the velocity vector or the tangent vector to the curve at point P. Up to now, we've been calling it tangent vector. Now, when t represents time and your r represents displacement, we can refer to that as a velocity vector. Note that this is the same limit used to define r prime, so the direction of r prime gives the direction of motion at time t. Moreover, the magnitude of that velocity vector, magnitude of r prime of t, is the magnitude of x prime of ti equals y prime of tj, which would be the square root of x prime squared plus y prime squared. That would be what we call the speed. Speeds are always positive. Your velocity vector may not always be positive. It may be going in the opposite direction of what you would normally have thought, and so that it could have a negative characteristic to it. Speed, though, is never negative. Could be 0, but never negative. All right. Similar to how r prime of t is used to define velocity, you can use r double prime of t to find acceleration, as indicated in these definitions. X and y are both twice differentiable functions of t. Before all it needed was 1, now it needs to be twice. And R is a vector value function given by R of t is equal to x of ti plus y of tj. And hopefully you can see to extend this to 3 dimensions, just do a z of tj, k. Okay? Then the velocity vector, acceleration vector, and the speed at time t are given. The velocity vector is r is v of t, which is r prime of t, which is x prime of ti plus y prime of tj. If you had space, you just extend that to plus z prime of t k. Acceleration, a of t, would be r double prime of t, which would also be v prime of t, and that would be x double prime of t I plus y double prime of t j. And the speed goes back to the velocity vector, and it's the magnitude of that first derivative of your displacement vector. It's the square root of r prime of x prime squared plus y prime squared.
Right.
We are. How could it be? We were just beginning to have fun. No, we were always having fun. Okay. We will start next time with this slide right here for motion along the space curve, right there on page 837. Don't think we got enough in 12.3 for any new homework exercises, so just do, I think there were plenty in 12.2, weren't there? Okay. You can live with that. Okay. And we'll pick up and go from there next time. Any questions? All right.